Okay, last lecture we started this power transformer example, and we need to find the voltage of the source and the current of the source. So I would say like Vs and Is. So how we can find the current or the voltages? Basically, most likely starts or make the notations, voltage notations, which is V1 bar, V2 bar, I1, I2, such that the positive will be at the dot side, the current enters the dot side. Then start from the extra given information. When you look at the extra given information, we have a load. We assumed a current of the load going down to make sure we will not go through the negative sign of the power. So we just want to make sure that this load is absorbing power. So in order to make it absorbing, the current must enter the positive sign, so I can avoid the confusion. So every time when I do this with the load, I need to assume a current of the load such that it goes into the positive sign of the voltage. Then we have the power. So some power information, we converted the power to complex power. Then from the complex power, we can find the currents, which is S over V conjugate. Then we calculated the current IL. After calculating IL, what's the relationship between IL and I2? They are the opposite of each other. And the opposite means negative sign. Negative sign in rectangular coordinates. But in polar, we will put 180 degrees phase shift. That's the difference. So in polar, negative 16.26 plus 180 degrees phase shift, it will be 163.74 degrees. Or in other words, if you are afraid to make confusion, you can say 0 minus 50 angle, negative 16.26, so the calculator will give you the answer. Okay? So after calculating the currents, we know I2. Let me relabel here the voltage. Here is V1 bar. Here is plus minus V2 bar. Here is I1 bar. Here is I2 bar. Then we have here IL bar, and here is plus minus VI bar. So far we calculated IL, we calculated I2. How to calculate I1? Using what? It is after the transformer, or there's a transformer in the middle. Then we need to use the transformer equations. What are the transformer equations? We have current formula, voltage formula, power formula. Which one is better to find the currents? Current formula, right? So we will say that we can use the current formula, which is N1 times I1 bar plus N2 times I2 bar equals to 0. So we need to calculate I1. So I1 bar will be negative N2 over N1 times I2 bar. Do we know I2? Yes. Do we know N1, N2? Not really. How can we calculate N1, N2? Look at the voltage formula. So the voltage formula says that V1 bar over N1 bar equal V2 bar over N2 bar. Or in other words, we can say V1, V2 ratio equal N1, N2 ratio. So V1, V2 ratio, which is 7.2, 240, equals to N1, N2. As a result, we can say N2 over N1 equals to 240 over 7.2 times 10, which is 7,200 times 10 power 3. As a result, we can substitute this here. This yields to be I1 bar equals negative 240 over 7,200 times what? I2, which is we calculated as 50 angle 163.74 degrees. Then the answer will be 1.67 angle negative 16.26 degrees. This is I source. Okay? Does this make sense? Using the current formula, then we realize the turns ratio, we don't know the turns ratio, then you can use the voltage formula to find it. Or you can basically, when you look at here, you can say this is N1 over N2. Even you can write it without doing the current formula. This is V1 ratio V2, the same thing as N1 ratio over N2. Then now we calculated I1. The next thing is to calculate V source. How to find V source? Try from the load side toward the source. How? So here, look at V load is given. It is given as 240 angle 0 degrees. What's the relationship between V1 and VL? Anybody knows? They are in parallel, they are the same, right? Or in other words, you can do KVL at this loop, and you can say KVL loop 2, negative V2 plus VL equals to 0, therefore V2 equal VL. Or in other words, they are in parallel, then 240 angle 0 degrees. Now, what's the relationship between V2 and V1? Transformer in the middle. So what I need to use what? The voltage formula of the transformer, right? The voltage formula of the transformer says V1 bar over N1 equals V2 bar over N2. As a result, we need to calculate V1, which will make it N1 over N2 V2 bar. And N1 over N2 is given as 7,200 over 240 times 240 angle 0 degrees. So 240 will cancel each other. So V1 as a result will be 7,200 angle 0 degrees volts. Okay? Now I calculated V1. What's the relationship between V1 and V source? Look at the circuits. Are those series parallel? What do you think? Are those parallel? Right. These are parallel. So we can say V source equal V1, or you can say, let's do KVL at loop 1. KVL at loop 1. This, which is negative V source plus V1 equals to 0. Therefore, V source equals to V1, which is 7,200 angle 0 degrees volts. Then problem done. That's all. I just calculated V source, I calculated V1. Any questions? Yes.
On the exam, are we allowed to just say they're equal to each other, or do we need to show with KVL that they are?
You didn't need to show. If they are in parallel, just say in parallel.
And that's it.
Here, just I oversimplify it, just to make sure to prove they are in parallel, in case if you didn't get the idea. Any other question? Okay, let's do example number 4. This is the last one in the power transformer. Now the problem is getting more complicated. How? We have these two impedances in the middle. So what should I do? Almost very similar in procedure for example number 3. But there will be slight differences. So we need to determine V source, Vs, when V load is 240. So we have V load 240 degrees, angle 0. Now we need to determine again V source. What should I do? The first step before doing anything, make sure is the voltage polarities, are the voltage polarities and current directions given? No, they are not given. Assume your own, or you assume based on the our rules, how do we define the voltage polarities and current directions? So we'll make the positive at the dots. Here's V1 bar, positive at the dots, V2 bar. Then the current enters the dots. So here is I1, here is I2 bar. Okay, does this make sense? Then start from the extra given information. Extra given information is the load voltage and the load impedance. How can we use this? We know the voltage, we know the impedance. We can find the current using Ohm's law. Is this correct? Yes. So in order to apply Ohm's law here, I don't want to go through the negative sign of Ohm's law. What should I do? I'm going to assume a current of the load enters the positive, and then I can guarantee Ohm's law will be positive. So again, I don't want to be confused. Should I put negative or positive sign or in Ohm's law? Then that's why every time I'm going to assume the currents enters the positive polarity of the voltage. That's why I assume my own current. Then after calculating IL, I can find I2, the relationship, if they are in the same or the opposite. I just put negative sign or 180 degrees phase shift. So start from the extra given information, which is start from the load toward the source. Okay, we'll go backwards. Then basically we can say Ohm's law IL will be VL over RL or ZL, whatever. So VL, which is 240 angle 0 degrees divided by 23. So the answer will be 10.43 angle 0 degrees amperes. This is IL. Then, what's the relationship between IL and I load? IL and I2, I load and I2, those are the opposite direction. Those are in the opposite direction. And opposite direction means negative sign. So we can say I2 equals to negative IL bar. Therefore, negative sign means 180 degrees phase shift. So it will be 10.43 angle 180 degrees phase shift ampere. So that's I2. Then I can find I1 by applying the current formula. So you can see here is I2, here is I1, and we see the turns ratio as given as here. Here is N1, N2, 7,200 over 240. Then we can say, apply the current formula. Let me write it here. N1 times I1 bar plus N2 times I2 bar equals to 0. Therefore, I1 bar will be negative N2 over N1 times I2 bar. Then it is negative N2, which is 240 over N1, 7,200 times 10.43 angle 180 degrees phase shifts, phase, which is the answer will be 0.35 angle 0 degrees ampere. This is I1. Okay? Now, I calculated all of the currents. I calculated IL, I2, I1. This is very similar to what we did in the previous example. Now, the next thing is to calculate the voltages. Start from the source toward the load toward the source. How to calculate the voltages? Let's try to plan our answer. Let me have a look here. Zoom. Then, do we know, basically before in the previous example we said V2 and VL are equal to each other because they are in parallel, right? That's what we used to say. Or we said we can apply KVL. Here, in this example, they are not in parallel because there is this impedance in the middle. This causes the problem. So what should I do? Do KVL. So let's do KVL, this loop. So your KVL loop 1. I'm going to assume here is a voltage polarity for this part, so I'll make it as negative positive V line 2. Why I make it negative positive? Because I want to make sure this is I load, I2. I2 enters the positive polarity of the voltage, then I make sure Ohm's law is positive. So KVL loop 2, it is negative V2 minus V line 2 plus VL, all of them bars equals to 0. We need to calculate V2, so V2 bar will be negative V line 2 plus VL bar. Substitute V line using Ohm's law, which is I times R, so it was negative I2 times Z bar, Z line 2 plus VL. Now substitute them, which is negative I2. We calculated it as 10.43 angle 180 degrees times Z line, which is 0.02 plus J 0.022 plus V line 240 angle 0 degrees. Then the answer will be for V2 will be 240.21 angle 0.05 degrees. This is V2. And don't forget the unit, which is volts. Okay? Then here now, let's redraw the circuits for your demonstration. So here is plus minus V2, here is I2 bar, here is IL bar, Here is plus minus V1 bar. Here is I1 bar. So far we know IL, we know I2, we know V2, we know I1. And here we assume this as plus minus, or actually minus plus V line 2. Here is, we just calculated V2, how to calculate V1 using the voltage formula, right? So the voltage formula, again, how can I know I need to apply voltage formula or I need to apply the current formula? You need to find the voltage formula. You need to find the current formula. And the same thing, which is whenever you see the transformer in the middle, you need to use one of the transformer formulas. Okay? Because V1 in one side, primary side, V2 in the secondary side. Then definitely I need to use the transformer formulas. And the same when I say I1 in the primary side, I2 in the secondary side, then definitely I need to use the transformer formulas. Okay, how to calculate V1 using the voltage formula, which is V1 bar over N1 equals to V2 bar over N2. So as a result, we can say V1 bar equals to N1 over N2 times V2 bar. N1 7,200 over N2 240 times V2 bar, which is 240.21, angle 0.05 degrees volts. Then basically, after doing the calculation, V1 will be 7,206.3 angle 0.05 degrees volts. This is V1 bar. Now I'm not done yet because I need to calculate V source. So after calculating V1 bar, how to calculate V source? We need to do KVL at loop 1. In order to do KVL at loop 1, we need to assume a voltage polarity for the impedance, which is this impedance. How to assume the voltage polarity? We need to make sure Ohm's law is positive. So the current enters the positive. Since the current traveling clockwise, therefore I'm going to make the positive here, the negative here. Then I can call it V line 2, V line 1. Okay? Again, I need to make sure Ohm's law is positive. The current traveling clockwise, therefore I make the positive this way. So let's do KVL loop 1. Start from the left bottom corner, then travel clockwise. Negative V source plus V line 1 plus V1 bar equals to 0. Then V source will be V line 1 plus V1 bar. Then substitute V line 1 as I times Z. So it will be I1 times Z line 1 bar plus V1 bar. Now I'm ready to substitute the values. I1, which is 0.35 angle 0 degrees, times Z line, which is given as 18 plus J20, plus V1 bar 7,206.3 angle 0.05 degrees. Then when you substitute this like this in the calculator, you will get V source equal to 7,212.6 angle 0.11 degrees volts. Then problem done. We just calculated V source. Okay? Any questions? There's a textbook problems, recommended problems, which is problem 8.13, 8.16, 8.17, 8.21. Okay. And by the way, I think you are aware that quiz this week, it has been moved to I think after the exam. So quiz number 19 was quiz number 9 was supposed to be Wednesday, April 3rd, but it has been shifted to April 24th. Okay? Because next week there will be exam. April 17, quiz 10. Then April 24, I wrote in the syllabus as a backup. So quiz 9 has been shifted to April 24. So any question about the power transformer? Okay, so these 4 examples are are very important in applying how to apply voltage formula, current formula. Power formula, I think we might not use it a lot, but most likely it's mainly in voltage and current formulas. Then these textbook problems are highly recommended, so you can try them. Sometimes you can see the answers, because since I posted the answers have been posted in different way than or the different way that what I used to do. Basically, some other analysis, they used to something we call it refer these from this side, move it to the other side, from primary to secondary or secondary to primary. We haven't covered this, so whenever you see anything in the textbook, refer impedance from primary side to secondary side or the vice versa, forget about it, okay? This is one technique that's been used in electrical machines, and this technique is very effective, but not for our course. I don't want to make it too complicated on you. Okay, now the next topic. So there's again a pre-recorded lecture about overview, power system overview, power electronics overview. And after that, which is the electrical machines and life. So I'm going to go through basically the topics called the generator. Okay, so there's a topic or something, a course even in electrical engineering, or sometimes they've been taught in several, they used to teach it in several courses, called electrical machines. So the electrical machines can be either static or dynamic machines. Static, no moving parts. As an example, the transformer is an electrical machine and it's not moving. Then we have another type called dynamics. Dynamics machine, basically there is a moving parts. Since there is a moving parts, it can be split into 2 areas. That moving parts can be linear motion or it can be rotating. Then also it can be split into other ways, which is it can be as a motor, it can be as a generator, it can be as exciter. So the motor can be rotating or it can be linear. What's the example of linear motion? I mean, we know the motor is rotating, most likely. What's an example of linear motion? Sometimes in some industrial loads, when there is, for example, a manufacturing line on something like a machine moving up, down, for example, to close the lids of something, up, down, when there's a production line, or left, right. Other than that, which is something like electric train, there is a magnets, North Pole, South Pole, and the train in the middle. Then it's moving in a linear motion. So which is moving up, down, or left, right, whatever. While rotating motion, moving in rotation. Okay? So the vast majorities are based on rotating motion, like motors. And then we have a generators. What's the difference between motors and generators? Motors converting electrical energy to mechanical energy, right? Generators converting mechanical energy to electrical energy, which is the opposite. The structure of the motor and the generator are very similar. But maybe the thing which is the power flow. Or am I using mechanical to electrical or electrical to mechanical? Then in any rotating thing, which is there is something we call it stationary parts, non-moving parts. Then we have a moving parts. So the stationary part is called stator. Then there is a moving part called rotor. These 2 are moving. Before discussing the generator first, like today's lecture, we will go through the generators. But before discussing the generators, how is the overall principle of the electricity being generated, or how is the motion will be occurred if there is electricity. So whenever there is mechanical energy, can I convert any mechanical energy to electrical energy by just connecting two wires and that's it? The answer is no. Can I, if I put electricity to any device, will it rotate? No. There should be something. What's that thing that makes the motion or makes the electricity to be generated? Any thoughts? There is a device, even like in the small DC motor, and any small motor, you can find it that makes something happen or rotate. What do you think? Are you familiar with the small DC motor that was in the toys? Have you ever tried to open it? What's the first thing when you open? What did you see? Inside it's inside the metal. Magnets, right? Do you remember? That magnets will do what? Produce a magnetic field. So the magnetic field is very important in the power generation or in the motor as well, in the motoring. So the point is the magnetic field. Magnetic field can be either from the magnets or it can be from the source that will produce a magnetic field. Okay, who says that? Or based on what we build this? Are you familiar with Faraday's law? A little bit from physics too. But here is like the summary. Faraday's law. I'm going to go through the summary. So whenever we're having a moving parts, magnetic field, and electrical currents. So we have three things. If any of these two exist, the third one must exist. Which is basically, when I have, here I'm not going to call it as number one, here is number two, here is number three. When I have number one plus number two, I have moving part and magnetic field. This must produce number three. Must. And this is the concept when there is moving parts, magnetic field will produce electricity. This is what? Generator. Is this correct? Okay. When I have magnetic field plus electrical currents, this will produce a movement. And that movement is the motoring action, right? So we can say that whenever you have a moving part alone, without a magnetic field, you cannot produce energy. You cannot produce electricity. You need to have a magnetic field. The other way, or the other thing, whenever you have electrical currents, put it to any device, it will not rotate, it will not move. When will it move? When you put a magnetic field. So it's a must to have a magnetic field. You can recall physics 2, Faraday's law and Lorentz law, etc. And how's the object when it's the electron when it enters a wire, there is a magnetic field, it will cause the wire to rotate. There is an experiment that you did in physics about this. So here is the summary. We need to have a magnetic field. So the key is the magnetic field. Okay, without a magnetic field, I cannot produce electricity. But there is something that we can say interesting. Since Faraday's law says, if we have any of these two, this will produce the third one. So when I have electrical currents, magnetic field will produce mechanical energy. When I have mechanical energy, magnetic field, this will produce electrical currents. How about if I have electrical currents and movements, or in other words, electrical currents and mechanical energy? What will happen? This will produce a magnetic field. This is something interesting. So when I have 1 plus 3, this will produce 2. So producing a magnetic field without the need of using a magnet. This is called exciter. Okay. And this is used a lot in very large generation very large motors. So in some applications of electrical machines, where sometimes we don't have a magnet in the structure. Okay, any questions? Now let's go to the conventional or the traditional power generation. Again, to generate power, you need to have a magnetic field plus mechanical energy. This will produce electricity, which is electrical energy. Now, we have many types of generators. We have something based on single phase. We have three phase. So these generators based on many factors. Single phase generators, like the generators that we are using it, for example, when you go to like a park where there's no electricity, then you rent a generator for your event, whatever. That's based on single phase. Then we have some other type of generators based on three phase, etc. I'm going to discuss the conventional thing, which is the conventional based on what we see in large scale, which is to supply the cities, or that's generator being used in the power plants. That's what I mean by the traditional or the conventional generator. So it will be based on three phase. And the other thing, which is we have different types of generator, like it's called synchronous. We have something called induction. Most likely, synchronous is used for fixed speed applications. Fixed speed, fixed frequency. So on large scale, the speed of the generator will be fixed. The frequency is 60 Hertz, which is fixed. Therefore, the best thing is to use the synchronous. While the induction can be used for variable speed applications. Like what? You can imagine that you have a wind turbine and the wind speed can be changing, can be varying, right? So this will make, we need to have a generator that's capable of handling variable speed applications. Therefore, we can use as an example induction generator in wind turbine applications for renewable energy. While for the traditional, where we can generate electricity from fossil fuel, which is from the power planets, combined cycle, single cycle, whatever, you have this, the output of it, which will produce a rotation. That rotation from the turbine will rotate. It will be connected to the generator. That generator, for the traditional thing that's used to supply or for real power in the big power planets, is based on three-phase synchronous generator. Again, that's what do we mean by the traditional generator, which is three-phase and synchronous. Let's go to the notes. This topic is not in the textbook, so that's why I called additional notes. The traditional AC generator. Okay. Again, the traditional AC generator, we mean by this, which is three-phase synchronous. Synchronous, again, for fixed speed applications, for fixed frequency. The frequency is 60 Hertz. We need to have the constant speed. Then this is the best application. How does the generator look like? It will be very large, very huge, because it's been used for supplying cities, or supplying large, very large areas. So this is the image of it, the picture of it. So you can see how big it is, and it can be maybe larger size than this room. Okay, so this component has is very complicated. There are many factors associated with it. So our target is to focus more in the electrical parts, focus more in the steady-state analysis. We don't want to discuss the transients. We don't want to discuss any type of the behavior. So we want to make sure how the overall thing will be with the generator. So let's just discuss a little bit about the generator. Again, we mean the three-phase synchronous machine. Basically, generator converts mechanical to electrical, motor converts electrical to mechanical. Then the generator will be, there will be two parts, or any machine, not only the generator. There will be stator and rotor. But for the synchronous, or the generator, synchronous generator, this part, the moving part is the magnetic field. Is a magnet, actually. And coils are on the station. So basically, you can imagine it like, where is the stator, that's non-moving part, where the electricity will be produced. There are coils. Coils means number of turns around the core. Something similar to what we discussed at transformer. Then the electricity will be produced there. So what will happen? The shaft is connecting to the turbine. I'm sorry, the turbine, which is, there is a moving, then connected to the generator. So the rotor starts rotating because of the mechanical energy. When it starts rotating, the rotor, inside the rotor there is a magnet. That magnet there means there is a magnetic field. So as a result, you have a magnetic field, you have mechanical energy or moving. This will produce electricity according to Faraday's law. Then the third one must exist, which is the electricity. Then the electricity will be produced at the stator, which is at the coils of the stator. Then this will go through this. That's again how the structure looks like. Since it's three-phase, and this is something we call a two-pole, this means we have one north, one south. This is two-pole machine. So we will make that complicated device that we see here just to convert it to look at the steady state and the electrical part structure. We don't want to discuss some other impacts just by assuming everything is working fine. Then what we are worrying is just look at this part. This is not 100% the true, but I'm focusing on this, assuming the other factors are constants, then we can be negligible. So we have, look at this. You can see we have A, B, C. A, B, C. As we know, there's live and neutral, or there's positive part or negative part, which is something for producing the positive, or the current will go, something will for the currents to back, right? For any wall plug or for anything, you need to connect the other side. So that's why we have A bar and A. So you can imagine the dots is like an arrow go to your face or out of the page, and the cross like go an arrow. You see the tail of the arrow goes down or into the page. Okay, which is go up and down. That's how it is. And basically it will be rotating. So we see that there is A bar, B bar, C bar. These are because these are based on three-phase. Then there is a magnet, live and neutral, and that magnet is rotating. Since this magnet is rotating, there is a moving and there is a magnetic field. According to Faraday's law, there will be the voltage will be induced at the coils at A, B, C. So the voltage will be induced, which is something we call this a flux linkage, a sinusoidal flux linkage because of the rotation of the magnets. Then will produce the voltage. Then we can say that that magnet will complete one rotation in a specific period of time. So one rotation needs 360 degrees. Okay, to complete one rotation. So whenever we say the frequency is 60 hertz, this means 60 revolution per second. So that generator, for two-pole generator, this is rotating 60 revolution per second. Most likely, revolution per second, or in other words, RPS, we don't use it a lot. For the fifth speed, we used to use RPM, right? Which is revolution per minute. So how to convert RPS to RPM? So you can say the speed in RPM will be the frequency times 60, which is 60 times 60, 3,600 RPM. As a result, I mean RPM, no matter if it is uppercase or lowercase, I'm making them uppercase. As a result, for the two-pole generator, in order to produce a 60 hertz frequency, it needs to rotate around 3,600 RPM, and this speed must be fixed at that. If it is not, it will produce different frequency than 60 Hertz. In other words, the frequency and the speed of the generator are very related to each other. Okay? The speed of the generator determines the frequency. That's why we say synchronous is suitable for constant speed, constant frequency. So we need to have a device that works only at that constant speed. Okay? Now, sometimes we can say for very big generators, if that generator, for example, rotates at 3,600, this is fast speed, maybe there will be vibrates, there will be some losses, or something like that. So it can be unsafe operation. Can we make it slower speed than that? The answer is yes. How? By increasing the number of poles. So here is something we call a 4-pole machine. 4-pole machine, basically, this is based on, we have 4 poles, north, south, north, south. So you can imagine, let's make our observation points at A. So we started from the north. When it goes to south, it will be 90 degrees. Goes back to north, 180 degrees. So we realize that we can complete one cycle by only traveling 180 degrees. So there is no need to travel 360. While this is in 4-pole. While in 2-pole, we used to travel 360 degrees. This means when you add the other 2-pole, we can reduce the speed by half. Because it is just enough to go 180 degrees to complete one cycle, then the speed can be reduced to 1/2. So as a result, we can say the speed can be 60, or the frequency, times 60 times number of poles over 2. That's the relationship. So this yields to be 60 times 4 over 2, which will make it 1800 RPM. So in order to satisfy 60 Hertz frequency, we need to have 1800 RPM, other than 3600, which reduce the speed a lot. Okay? So now we get a little bit some confusion, which is sometimes we need to have 1800 RPM, we need to have almost 3600 RPM. As a result, we get some definitions like something is called NM, something is called NE. So by the way, the speed in RPM, we will call it N as a speed. Then we have something we call it NM, which is the mechanical speed. Basically, this is the actual speed. Then we have the electrical speed. So the electrical speed related to the frequency and number of poles, not related to poles, which is, don't worry about poles here. Don't care about poles. While the mechanical speed include poles. What do I mean by this? We can say the electrical speed is actually frequency times 60. Mechanical speed, it is electrical speed times number of poles over 2. So in other words, for 2-pole machine, F times 60 times 60, 3600 RPM. For mechanical, 3600. How about 4-pole machine? 4-pole machine, electrical will be 3600, then mechanical will be 1800. How about if we have 8-pole machine, 8-pole 3600, then here I think around 900, something like that. So in summary, we realize the electrical speed is not changing at all because it is based on the frequency, constant frequency, while the mechanical speed is changing. Okay? So now I encourage you go to the entrance of a Brown Hall in the downstairs. Then at the entrance you will see a big machine, which is here. This is the generator. That was the traditional generation that has been used in 1920s, or I think it started service in 1890s. then you can have a look how the three-phase generator looks like. This is something similar to this. I encourage you to look at the data sheet. Then next lecture we will continue